So this is going to be me working out these practice problems with you of I know that some students have been asking for this and I do think that it helps. So I'm just going to go through them in every single order that is the same as your assignment on Canvas, and I would love for you to follow along with me. So problem number 1 says that the sun is approximately 1.5 times 10 to the 11th meters away from Earth. Given that the speed of light is 3.0 times 10 to the 8th meters per second, how long does it take light to travel from the sun to the Earth? We want to give our answer in seconds and then also in minutes. So the way in which we think about this is first you got to think about what are your values that you have. And you have two specific values, and you need to determine based off the units what exactly you are measuring. So the first one that you have is 1.5 times 10 to the 11th meters. Now, the idea here is that if you have the unit meters, this is going to represent a displacement. And then finally, you have a 3.0 times 10 to the 8th meters per second. With the units meters per second, this is a velocity of a wave. So if you have an equation that has a displacement, how far it is, and then also a velocity, and you're trying to figure out time, your answer in seconds, then there's only going to be one equation. And that equation is that your velocity equals your displacement divided by your time. Now, we want time by itself. So what we need to do is that we need to rearrange this equation in order to figure out for time. So we multiply it on both sides here. It cancels out. You get time multiplied by velocity equals your displacement. And then here we want to get time by itself. So I am going to divide both sides by velocity. It cancels here. And then finally, your brand new rearranged equation is that time is equal to your displacement divided by your velocity, which will work out nice. So now all we have to do, we need to plug it in, is that time equals our displacement we have is 1.5 times 10 to the 11th meters, and then our velocity that we have is 3.0 times 10 to the 8th meters per second. If we go and we divide these values, and again, I want you to follow along with me on your calculator because you know how aggravating your calculator can be sometimes with these scientific notations, then you should get a value of 500 seconds. So 500 seconds. Now, there is one problem here. It's that this is a math problem, and with math problems, we always have to take a look at sig figs. Our sig figs here, we have two sig figs for the top, and then really the bottom is more of a given, but we could even count it as two sig figs in this problem. So our 500 seconds right now, this has one sig fig, and we need to turn it into two. So there's two ways in which I've taught you how to do that. The first way is to go and to write the line over and say that it's 500 with this 0 being the last one that is significant. But my preferred method is always just going to be turning it into scientific notation, 5.00 times 10 to the second seconds. So there's our answer in seconds, but now we want to get our answer in minutes. So what we do is we have a conversion, 5.0 times 10 to the second seconds, and to get it into minutes, all we need to do is we need to cancel out seconds. To get it into minutes, we say that it has 60 seconds in 1 minute. Our seconds cancel, and then in the end we get our 5.0 times 10 to the second divided by 60, and we get 8.3 repeating minutes, but with two sig figs is 8.3 minutes. So 8.3 minutes, and then this 5.0 times 10 to the second seconds are your two answers for problem number 1. Let's go on to problem number 2. It says that the string below is 6 meters long and is vibrating as the third harmonic. Again, you can tell the harmonic by the number of antinodes. This has 3 antinodes, meaning that your harmonic is the third. The string vibrates up and down with 45 complete vibrational cycles in 10 seconds. Determine the frequency, period, wavelength, and speed for this wave. So let's first figure out what we want to do. Is that eventually I'm going to need to find the frequency, the period, the wavelength, and then finally the velocity or speed of this wave. In order to do this accurately, I'm going to start thinking of this problem really does make you think about what the definitions of each one of these values are. So let's start out with frequency. The definition for frequency is always just going to be how many waves per second. So I'm going to write waves per 1 second. Anything over this 1 second is going to give you the value hertz, which is what we want to do. Here we have 45 complete cycles in 10 seconds. To get 45 cycles in 10 seconds, so 45 cycles in 10 seconds, and we want to get it over 1, then what we need to do is we need to divide both sides by just 10. That way we're going to get 1 second, and here is going to give us our frequency, which in the end is going to be 4.5 hertz. So we have our frequency, which works out nicely as 4.5. We check our sig figs, 2, 2, 2, all good there. For period, what we want to do is period you could have solved in one of two ways, and I'll show you both ways. The first way that I would do it is I would do 1 over your frequency. And if you do 1 over your frequency, you do 1 over 4.5 hertz, and you solve your period as 0.22 seconds. That would be mathematically, but if we want to think about it, again, just by definition, the period is how many seconds per wave that we have. So if the whole thing takes 10 seconds, and we had 45 waves, then the idea is that if we take 10 divided by 45, again, you're going to get your period of 0.22 seconds, which, again, works out nicely as long as these two values match. Then, wavelength. Wavelength, you can think of it a couple of ways. Number one, this 6 meters is not the wavelength. The wavelength is always from one spot to the same exact spot. So what I mean by that is, notice I went along and did the wavelength of this entire wave. This value right here is your wavelength. But you have a standing wave, and you have an equation for the wavelength of standing waves. It's 2 times the length divided by n, and n represents the harmonic. So here, the length of your string is this 6.0 meters. So I take 2 times 6.0 meters, and I divide it by the n, and n is that you can notice two things. A, it tells you it's the third harmonic, or B, since it has 3 antinodes, 3 points of very, very large amplitudes, your harmonic is 3. So 2 times 6, 12, divided by 3 is 4, so a wavelength of 4.0 meters with my 2 sig figs. Then, finally, your velocity you could solve in one of two ways. You could either do velocity equals wavelength times frequency, or your velocity is equal to your wavelength divided by your period. Either way is going to be perfectly fine. I'm going to use this one, the velocity equals wavelength times frequency, because I think 4.5 is a nicer number than 0.22. So if I want to solve it, I'm going to say velocity equals my 4.0 meters multiplied by my frequency of 4.5 hertz of 4 times 4, 16. 4 times 0.5 is 2, so 16 plus 2 is equal to 18 meters per second. That's going to be your velocity. You have your period, your frequency, and then your wavelength. These are going to be your 4 values for problem number 2. Problem number 3 is our planet problem. And it says, like all planets, the planet Venus orbits the sun in periodic motion and simultaneously spins about its axis. Just as on Earth, the time to take one complete orbit, the period of orbit, is what defines a year. It's how long it takes to go around. And the time to make one complete revolution around its axis, literally the planet spinning, is what defines a day. The period of orbit for the Earth is 365 days, 0.25, because again, we have a leap year every 4 years, and the period of rotation is 24 hours, which is what we call one day. But when these same values for Venus are expressed relative to Earth, Venus has a period of orbit of 225 days. That means that Venus's year is 225 days, and Venus's actual like day, quotes day, is 243 days. So a day is longer than a year in Venus. I want you to determine the frequency of orbit and the frequency of rotation in hertz for Venus. So here's what we're going to do, is that if I want frequency, no matter what, frequency is always going to be 1 over your period. That's how you're going to try to solve for these on either one. And if I want my periods, I have a period of orbit of 225 days and then a period of rotation of 243 days. If I want this in hertz, I want you to think, what in the world is the unit for period? And period is an amount of time. The SI unit for time is seconds. So what we need to do first is that I'm going to write period of orbit, capital T, is equal to 225 days. And I need to get this into seconds. So I'm going to have a really, really long conversion here. So what we want to do is, first off, let's cancel out days. So days, and I don't know how many seconds are in a day, but I do know that 24 hours are in one day. So my days cancel. Then I'm in the unit hours. I know that 1 hour is 60 minutes. So hours cancel. And then finally, I know that in 1 minute, there are 60 seconds. So now minutes cancel. So the idea here is if I take 225 times 24 times 60 times 60, I am going to get my value in seconds, which is what I'm going to do. So 225 times 24 times 60 times 60. And I get 1944 and then 4 zeros afterwards, seconds. So 1944, 1, 2, 3, 4 zeros afterwards. Now, I need to do sig figs because I started out with 225 days, meaning that my final answer in seconds is going to be 194. This second 4 is going to drop down to a 0, and then my 4 zeros after 3, 4 seconds. So 1, then 1, 2, 3. So 19,400,000 seconds is going to be my period of orbit in the correct units. If I do the same thing of my period of rotation, I'm going to take the exact same conversion and just do it again because I have days and I want to do it or get those days into seconds. So 1 day is 24 hours times, now I'm in hours, 1 hour is 60 minutes. Again, multiply out the minutes, 1 minute equals 60 seconds. Cancel out all my units, make sure that everything cancels because they're on opposing sides, and then I just multiply. So now I have 243 times 24 times 60 times 60, and I get, oh, that's a big number. All right, let's do it. 20995 200 is my calculator answer for the amount of seconds that is my period of rotation. But now I need sig figs. So what I'm going to do, I started out with 3 sig figs here. I need 1, 2, 3. This 9 is going to round up, making that 9 round up. So I am going to have 2, 1, 0. Correct? 2, 1, 0. Yep. And then 1, 2, 3, 4, 5 zeros afterwards. 1, 2, 3, 4, 5 zeros afterwards. Now, you might be thinking to yourself, Mr. Tate, that's not right. That's only 2 sig figs, and I would agree, which is why I'm going to draw a line above that 0 to represent 3 sig figs. Then, if I want my frequencies, because that's the end goal, frequency of orbit and frequency of rotation, I just need to plug it in as my frequency of orbit is going to be 1 over my period of orbit, which here is going to be 1 divided by my 19,400,000 seconds. And this is going to be a very, very small number. So 1 divided by 19,400,000 equals 5.15 times 10 to the negative 8th times 10 to the negative 8th hertz. And then finally, the same exact thing, my frequency of rotation is going to be 1 divided by my 21 million seconds, 3 sig figs, and I am going to get 21, 1, 2, 3, 1, 2, 3, 4.76 times 10 to the negative 8th. 76 times 10 to the negative 8th hertz. Again, very small numbers, but this value is your frequency of rotation, and this value is your frequency of orbit, both in hertz. So it's just a conversion problem. All right, problem number 4 is that Sachi is rocking to her favorite radio station, 103.3 FM. The station broadcasts radio signals with a frequency of 1.023 times 10 to the 8th. And then that should be hertz. Oh, my bad. The radio wave signal travels through the air of 2.997 times 10 to the 8th meters per second. Determine the wavelength of these radio waves. So let's again look at units. I have a frequency, so I'm going to write frequency equals 1.023 times 10 to the 8th hertz. And then I have a speed or a velocity. So I'm going to write velocity equals 2.997 times 10 to the 8th meters per second. So if I have a frequency and a velocity and I'm trying to solve for wavelength, there's only one equation for me. Velocity equals wavelength times frequency. And if I want to solve for my wavelength, I need to divide both sides by frequency. Cancels here, and to rewrite my equation, velocity divided by frequency is going to equal my wavelength. So let's plug it in. My velocity is 2.997 times 10 to the 8th meters per second, and divided by my frequency, 1.023 times 10 to the 8th hertz. And in the very, very end, I am going to get my value. So 2.997 e to the 8th divided by 1.023 e to the 8th equals, and I get 2.9296. So I'm going to write it first just as exactly my calculator says, 2.929618, and then lots of numbers after, and I need to decide sig figs. I have 4 sig figs at the top, 4 sig figs at the bottom, meaning I need 4 sig figs here. 1, 2, 3, 4. Draw my line, my 6 rounds up. Then, so I am going to have 2.930 meters is going to be my answer for the wavelength on number 4. Let's move on to number 5. 5 is saying that the standing wave pattern is established in a 246 centimeter long rope. A snapshot of the rope at a given moment in time is shown in the diagram below. Vibrations travel within the rope at speeds of 22.7 meters per second, and I want to determine the frequency of vibration of this rope. So there's a couple of things to note first about this problem. Number 1 is right here. You have a standing wave pattern, and for a standing wave pattern, you have one equation that can always be used for your wavelength, and that is right here. Wavelength equals 2 times the length divided by the harmonic. So there's one part. The second part is that you're trying to find the frequency of vibration. So let's try and figure out first what equations we are going to need. We need an equation with frequency and then velocity in it. And you only have one. It's that velocity equals the wavelength times the frequency. I'm trying to find the frequency. So if I start plugging in my knowns and unknowns, I can say that my velocity is equal to this 22.7 meters per second. That's fine. But my wavelength is not this 246 centimeters. Remember, wavelength is one crest and one trough until it hits the same value. This distance right here is going to be a wavelength. It's not going to be the whole thing. So what I need to do is I need to plug it into this equation in order to figure out my wavelength. So that's exactly what I'm going to do. I'm going to do wavelength equals 2 times my length, 246 centimeters, divided by the harmonic. And remember, the harmonic is the number of antinodes. So I have 1 here, 2, 3, 4, 5, and then 6. Remember, antinodes are the points of the highest amplitude here. So if you just count your amplitudes, then you will find the number of antinodes. So 2 times 246 is 492 divided by 6 is equal to 82 centimeters for my wavelength. So that works out nicely. My wavelength now is 82 centimeters, and I'm trying to determine my frequency as my unknown. So what I'm going to do is I'm going to rearrange this equation for frequency. So I need to go and I need to say that my velocity divided by my wavelength is going to equal my frequency, which works out great. I'm going to start plugging in my numbers, 22.7 meters per second divided by my wavelength, 82 centimeters. Now, you should see right now that there's a problem with this equation. One of them is measured in meters, one of them is measured in centimeters. You cannot plug this in yet. You need to convert. So, I can either convert those meters into centimeters, or I can convert those centimeters into meters. And I think that's the much, much, much easier thing to do. So I'm going to come down here, and I'm going to say 82 centimeters. And if I want it into meters, you need to know that the prefix centi, like cents in a dollar, years in a century, is 100. So I need 82 divided by 100, and I get 0.82 meters, which sounds fine. No worries there. So now we just go and we plug it again, or plug it in again, and we get 22.7 meters per second divided by 0.82 meters, and you get a value of 22.7 divided by 0.82, 27.6829, so 27.6829, and we need to decide sig figs. So you might be going and thinking, oh, this is 2 sig figs down here, but I actually messed up. If you notice, this 246 is my measurement. My 82 should not just be 82, it should be 82.0 centimeters to keep the sig figs with the same thing. So if I write it as 0.820 as the correct number of sig figs, I will need 3. And my value with 3 sig figs, this 8 again rounds up, and I am going to get 27.7 hertz for my frequency for number 5. Let's go on to number 6. Number 6 says that you count 17 complete waves pass a certain point in 120 seconds, and you measure 5.50 meters from a crest to a trough on the passing wave. What is the velocity of these waves? So let's first just start with my end goal. My end goal here is velocity, and I usually tend to use this equation, velocity equals wavelength times frequency. So I'm going to try that first and see what I get. So My first thing is a wavelength. Do I have a wavelength here? And you have to be really, really careful. This says from crest to a trough. I want you to think again, and let's see how well I can draw one. Ooh, keep on going, keep on going, keep on. Okay, not bad. A wavelength is always from one point of a wave to the same point in a wave. This is a wavelength, and right now my problem is saying that this distance is my 5.50 meters. Do you notice how I'm actually just 1/2 of my total wavelength in this equation right now? Because a wavelength has to be to points on the same wave. So think of it this way. Like, do you know if I like draw, let's call it a track, and like, have football goals on whatever, high school track. And with a high school track, if you start here, you only get to one lap whenever, if you run this direction, you get back to the original spot. It's the same thing in waves. You have to get back to the original spot in a wave in order to have a wavelength. So here, my 5.50 meters is 1/2 of my wavelength. And if I want to do it again, then I need to add 5.50 meters onto it again. So my wavelength for this wave, 5.5 plus 5.5, should be 11.0 meters. That's the starting point here, is 11.0 meters. Now, let's see if I can solve for my frequency of, again, frequency is how many waves there are per second, 1 second in particular. Right here, we have 17 complete waves in 120 seconds. So if I want 17 waves in 120 seconds, and I want 1 at the bottom, then I am going to divide both sides by 120. That's going to go, and that's going to give me 1 at the bottom, which is my frequency. So my 17 divided by 120 should equal my frequency. And if I do it correctly, 17 divided by 120, I get 0.1416 repeating. So 0.1416 repeating. Now, I need sig figs. 17 waves is not like a measurement. This is something that you just see. Oh, there's 3 rocks in this pond. It's just a value. Your measurement is 120 seconds, so I need 3 sig figs here. And my value with 3 sig figs is 0.142 hertz. So now I have a frequency, I have a wavelength. Let's plug it in. Velocity equals my wavelength, 11.0 meters, multiplied by my frequency, 0.142 hertz. And in the end, I need 3 sig figs, so I'm going to first plug it in, 11.0 times 0.142. I get 1.562 meters per second. So let's start out, 1.562 meters per second. I need 3 sig figs. So I look here, my 2 just gets cut off, and I have a final answer of 1.56 meters per second as my velocity. So that's number 6. Let's go on to number 7. Number 7 states that a dog whistle is designed to produce a sound with a frequency beyond that which can be heard by humans, between 20,000 and 27,000 hertz. If a particular whistle produces a sound with a frequency of 23,300 hertz, so I'm going to write that, 23,300 hertz for a frequency, what is the sound's wavelength? So I'm trying to determine wavelength. And then it says, assume the speed of sound in air is 331 meters per second. So my velocity is 331 meters per second. This is my idea. And if I'm trying to solve for my wavelength, again, the only equation that you have all 3 in is that your velocity is equal to your wavelength times your frequency. As soon as you get here, we're trying to solve for wavelength, so I'm going to divide both sides by frequency. Cancels here, and I rewrite it as my velocity divided by my frequency is equal to my wavelength. That'll work out nicely as long as I have all my values, and of course I do. So I have 331 meters per second divided by 23,000 hertz, and I need to come up with my answer. So 331 divided by 23,000, or 23,300 hertz actually, I get a wavelength of 0.014206, and then lots and lots of numbers afterwards. So let's decide sig figs at the very end. I have 3 sig figs at 23,300, 3 sig figs and 331. This value with 3 sig figs, that's a 0, is going to be 0.0142 meters for my wavelength of problem number 7. So one left. Let's do number 8. Earthquakes generate shock waves that travel through Earth's interior to other parts of the world. The fastest of these waves are longitudinal waves, like sound waves, and are called P waves. And a P wave has a very low frequency of around 0.050 hertz, so 0.050 hertz. If the speed of a P wave is 8.0 kilometers per second, I'm going to try to determine its wavelength. So let's first figure out all of my values. Again, your equation should be that your velocity equals your wavelength times your frequency. I'm trying to determine its wavelength, so I'm going to divide both sides by frequency. Cancels out here. I rewrite it as my velocity divided by my frequency equals my wavelength. Then I just need to start plugging it in. My velocity is 8.0 kilometers per second. My frequency then is 0.050 hertz, and I just plug it in. Now, remember, hertz is 1 over seconds, so my seconds match, so I can just plug it in as is. I don't have to do any converting for this. So 8.0 divided by 0.050, and I get 160 kilometers, which is fine for my wavelength to start out with. Now, if you want to go and you want to change it into meters, just so that, we've been working with meters this entire time, remember that kilometer means 1,000 meters. Kilo is 1,000. So here, if I want to solve, then I'm just going to have 160,000 meters for my wavelength. So 160,000 meters or 160 kilometers. Either one is going to be perfectly fine. So that's it. That's the very end of all of your problems. Please let me know if you have any questions. Thank you all.